everyone, and welcome to your lecture number 12 in the Real-Time Embedded System course. And today's lecture is the final one when it comes to the Real-Time Operating System section. Right, so last time we ended on a note and we spoken a little bit about the Pathfinder and the problem that happened over there, and it was caused by the use of semaphores, and we called the problems the priority inversion problem. And we tried to understand why this problem happened, and we were thinking of a solution for that particular problem. And the one of the solutions and the implemented solution that happened over there is to make sure that the tasks that doesn't need the semaphore should not preempt the low priority task that has the semaphore, instead to make sure that the highest priority task is not blocked for long because of the semaphore. And one solution for that is the implemented one is called the priority inheritance. This means that the low priority task, when it gets the semaphore that is shared with the high priority one, it will inherit the priority of the highest priority task that needs the semaphore to make sure that this one is not preempted, and hence it can give back the semaphore on time. Alright, so in today's recording we're gonna find out how to create different semaphore types using the free RTOS, what are the different function calls, and we're gonna discuss a little bit the ISR, the interrupt service routines, and this will be the end of our RTOS section. Alright, so one of the types of the semaphore, say, is a counting semaphore, and a counting semaphore can be seen as a queue that is, have a length of more than one. And in the previous lecture I said that typically we use counting semaphore, unlike mutexes for instance, to count something. So this is an object that is offered by the RTOS that is extremely fast instead of creating your own counter, right? So you can use the counting semaphore in order to count events or something like that. Fair enough? And we use those whether to count events, right, that are happening, and we need to keep track of them, and we can also use them for resource management, in the sense of every embedded system is made out of hardware part and a software part, and if we have a couple of components connected to our embedded system, so we're gonna keep track of them, of their use, and manage them. It could be a good idea to use a counting semaphore to see which one is taken, etc., and how many are left or available for us to be used. This brings us to a particular question that one might ask themselves is, what is the initial value of the counting semaphore? Well, there's no general rule. The idea is to see if we're gonna use them to count events, external events for instance, or we're gonna use them for resource management. So what do you think? An idea would be, for external events, for counting events, it makes sense to start from 0 and start counting, because we never know what's the maximum number of events that would happen, for instance. We can think about that. And for the resource management, for instance, we can start with a known number of how many resources we're trying to manage, for instance. Alright, so let's see an example here. So this is the syntax of and it's a human name so we can understand it. So apparently the system function call we're going to use is semaphore create counting. So there's the counting keyword here. And it has two parameters. The first one is what is the maximum number that we want to reach, and what is our initial count, right? So the max count can be seen as the length of the queue that we talked about, and the initial value whenever you're creating the semaphore. Fair enough? And of course the return value as the return value for a, I don't know, a task create, for instance, it could be something that happened or it failed. Fair enough? Alright, so check this out. So here's an example of a task, right, that is defining a semaphore here. So my semaphore, we're using a handle, and you should remember what that is. What is a handle? So it can be seen as an ID from the OS point of view. So a handle for my semaphore, I'm calling it semaphore. We good. And this is, I defined my semaphore. Now I need to create it. And here we can see that I'm attempting to create a counting semaphore, fair enough, with the maximum count of 10 and an initial value of 0. Alright, so this could be used for counting events, for instance. And then you can see that if it's not null, so this means that it did not fail, the creation of the semaphore did not fail, so I can do whatever I want to do later on. Alright, so let's see now. A second type of semaphores is the binary one. And if you remember quite well from my last recording, I was saying that a binary semaphore is halfway through between a mutex and counting semaphore, but still a semaphore is still a signaling mechanism as opposed to a locking mechanism that is available and made available using mutex. Alright, so this one can still be seen as a queue. However, this time it has the length of only 1. Alright, so it is created unavailable, and we can see that the function, the system call here, it's an easy one. All we have to do is create a binary semaphore. Fair enough. So we're seeing the example here. See, no parameters at all. All we have to do is create the, ask to create a binary semaphore and use the handle, whatever handle we're declaring here. Alright, so that's 1, 2, and those are 2 types of semaphores, the binary and the counting one. And the third type is the mutex. Alright, so as you can see, it feels the same thing. We need to declare a handle here, and then we're using a semaphore create, but this time it's a mutex. No parameters, fair enough, and the same protocol, so it doesn't differ a lot. However, as I said, this is important, so I'm gonna draw something around it. Right, it's implementing simple mutual exclusion. So this is the best choice to create mutual inclusion. This is a locking mechanism because it also supports priority inheritance, and priority inheritance is to avoid problems such as the priority inversion problem. Alright, and this is the name of the function call that we talked about here. Alright, this is an important remark here. So here I'm claiming that we cannot use mutexes from ISR, interrupt service routines, right? How come? Because remember last time that we said that the difference between the mutex and the normal semaphore, which is a binary or a counting one, is this one has some ownership associated to it. This means that the task that takes the mutex here is the only task that is allowed to give it back. This means that if something's happened, like an event, external event that I'm keeping track of, and it resulted in an interrupt, hence I need to go to the interrupt service routine that deals with it, And imagine that over there I'm trying to lock the mutex. This means that the only one who would be able to unlock the mutex is the internet is the interrupt service routine that was, the one who locked it. And I'll need to wait for the next event, so this will make my system freeze. Alright, so it's a bad idea. So never deal with mutexes inside interrupt service routines. Alright, so let's see. So we've seen that we can create a semaphore with 3 different types, so counting, binary, and lastly, but most importantly, mutex. Now the idea is, now I created it, so a task can take it, so can lock it or unlock it if it's a mutex. But for the time being, we're talking about the locking, so taking a semaphore, whether it's a binary, counting, or a mutex. Fair enough. So how does this happen? So alright. So the basic idea is, whenever I wanna take the semaphore, right, I can, if and only if it's available. If it's not, what would happen to me? Correct, I will go to the blocked state until it becomes available. Fair enough. Alright, so again, this particular function here, do not use it with ISR. ISR are delicate, so you need to handle it with care. We'll talk about it at the end of this particular recording. Right? And the full syntax of the semaphore take here. First off, we need to specify which semaphore we're gonna take, because we can imagine that in the program there are many semaphores associated to different components or different synchronization mechanisms that we might be using, right? So we need to get the semaphore ID, the semaphore that we're dealing with, and something else here, and we talked about it last time as well. So here, the text to wait, this defines the timeout periods. For instance, if the task is waiting for a semaphore, we can specify here that you can wait for it for an hour or so, and if if an hour passes and the semaphore is not given back by another task, we can imagine that we don't care about it anymore. We can just unblock and resume our execution. However, as I recommended last time, this should be set to infinity, because the protection mechanism that this enables, we have another protection mechanism that we talked about it a lot, and it's safer. We can use if something freezes, we can always use the watchdog timer and reset the whole system, and it's a better solution. Right, so this is the semaphore that we're trying to take, and this is the timeout period. If you wanna define it, we wanna use it. However, in order to set it to infinity, hence without a timeout, you can set it to port max delay. All right. So port max delay is as if you're setting your timeout to infinity. So your task will always be blocked and waiting for someone to give back the semaphore. All right. So let's say an example here. All right. So what am I doing? I'm creating, declaring a semaphore here. All right. And then I have task number 1, inside of which I'm creating a semaphore, and the semaphore that I'm creating is of mutex type. And then task number 2 has a perpetual loop attempting to take the semaphore that I created here. Alright, and I'm specifying the timeout period to infinity, so no timeout. Alright, so I'm gonna stay blocked until the semaphore is given, and hence I can take the semaphore, which is a mutex in this case. Alright, now let's find out how to give a semaphore. Well, with the syntax, it is rather easy. It's in the name, so semaphore give, and all we have to do is specify which semaphore we're giving back. Alright, so this is to release a semaphore, and again, do not use those with ISR. We're gonna find out why later. So let's see an example here. Perpetual loop. If someone is pushing a button, all I have to do is give back the semaphore. So using that, I'll be unlocking whatever semaphore I have here. Right, this brings us to something important. To the difference between a polling and interrupt based handling. So to handle events generated by sensors, so we can see those as external events for now. Right, so generated by sensors, and they can happen at any moment. So we have two schools of thought here. The first one is to keep on listening actively, keep on listening, listening to what's happening on the pin that is connected to the sensor, and this is what we call active listening or polling, right? This means that I'm gonna keep on checking if the sensor has yielded the wanted input yet, or something happened over there, yes or no, etc. Right? This is done actively. Or another school of thought would use the interrupts for that particular reason, and we've mentioned interrupts in last year's OS course and a little bit in the CA course as well. So an interrupt is something that happens and is considered to be something exceptional. Let's see. So imagine if a task, let's say, is executing and something happens, an external interrupt in that case we're talking about, because there are different types of interrupts. One of them is the exception that would happen from within the code itself, etc. But for the time being, we're gonna think about an external interrupt. So what would we do here? We're gonna pause whatever we're executing normally here. Alright? Go to the ISR, so interrupt service routine, that deals with the type of the interrupt here, and then once we're done with the ISR, we're gonna go back and resume whatever execution we had before. Alright? So this means that if I'm expecting something from outside, instead of keeping on listening what's going on outside, all I have to do is do something to know whether it's happening or not, right? Do whatever I do. Whenever this happens, whoops, I'm gonna come here, I'm gonna detect it and go and deal with it, and then go back to my normal execution. And this is an interrupt. Which one is better? Right, so I said this is keep polling, is keep asking. So this is you're gonna talk about it more in the tutorial. This is a listener, and the interrupt is stop the execution, go deal with it, and then resume whatever execution you had before. So yeah, this brings me back to my question, which is better, interrupt or polling? It's a big question. The answer is not that obvious. It depends on the context, it depends on the overall number of tasks you're doing in the system, etc., etc. So there's no best solution. There are two different ways to do something, and it really depends on your implementation, the system you're dealing with, etc., etc. All right. So let's see an example here. So this is something we're looking at and we did not see before. So imagine that this is part of an appendix in your somewhere, right? So we're discovering something new, something called attach interrupt. All right, so we already know what interrupt means here, and if we're any good in English, we would know what attach means. So yeah. And apparently here it's dealing with external interrupts. Awesome, we just talked about those, and let's read it together. So the first parameter to attach interrupt is the interrupt number. Normally you should use digital pin to interrupt pin to translate the actual digital pin to specific interrupt. For example, if you connect to pin number 3, use digital pin to interrupt as first parameter to attach interrupt. Alright, so awesome. So we've seen that at least the first parameter of this function right, is something that we need to specify to which pin we gonna detect an interrupt in, anyway, at which pin we're gonna detect if an interrupt is happening or not, or an event that would cause an interrupt is happening or not. Alright, so at least this one, and apparently we're gonna use some kind of translation function as we did, let's say, for the milli to ticks, because an OS only understand ticks, so we use some kind of translation function before, right? So this is a different type of translation. It's to attach the number of, to translate the number of pin to an interrupt number. Fair enough. And this is the first parameter. So at least we know that the first parameter of this new function that we're discovering here is to specify the pin on which we're gonna detect the event that might create an interrupt or be the source of an interrupt. Alright, so we know at least this parameter. So by now you should all have your boards, I think. I hope so. And if you're using an Arduino board, for instance, you can see that the pins that are available for you to attach interrupts at are the pin number 2 and pin number 3 and blah 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 blah. We don't care about those for now. Alright, so yeah, so an interrupt, so if an interrupt happens, we know by now that we should have some kind of ISR that will deal with the interrupt happening. Alright, so if we're creating an ISR, so it's a special function that has no parameters, because it's not a normal function in the sense of we're not going to do any additions and stuff like that in it, right? And they shouldn't return anything, of course, because their purpose is to deal with the interrupt that's happening. And this is why they should be as short as fast as possible, because remember, the whole idea of the interrupt is to go deal with it and then resume whatever execution we did before. So we need to be extremely fast. The shortest, the fastest. Fair enough? And this is what we're talking about. We're attaching to listen to generated interrupts from sensors, so from outside of our system. Want to see an example? Let's see an example. Alright, so let's check this out. I'm having some variable here for a pin, and this should ring a bell. Apparently this is the pin that I'm gonna use for the debug LED. Awesome. Here apparently I'm gonna use pin number 2, so most probably it's an Arduino board that I'm using here, and this is the pin that I'm gonna use to detect my interrupts. And I have some kind of variable for state set to low here, right? So we're gonna see what would happen here. So it's an Arduino language, so we have two things to deal with, the setup and the loop, correct, perpetual one. So in this setup, what I'm trying to do, yeah, of course, I'm gonna set my LED pin to an out and my interrupt pin, right, so number 2 here, yes, I'm setting it to an input, of course, because this is where I'm gonna detect something's happening, right? And I'm activating the pull-up resistor as well. Good for me. Alright, awesome. So let me do that. So let's check that function. So we've seen at least one parameter of it. Where is it? Voila. So we've seen at least one parameter. So the translation function with the number of the pin to get the interrupt number. We're good. And then, knowing what we know about the interrupts, right, we know that if an interrupt happens, this means that we need to deal with it inside an interrupt service routine. So we need to specify the function name of the interrupt service routine that deals with the interrupt. And here I'm calling it ISR. I could call it handler, I can call it ascend, I can call it, well, I don't know, star, whatever. So this is the name of the function that will be called whenever an interrupt happens here. And the event that will create my interrupt is a change. So if something changes on the pin, so on pin number 2, right, will cause an external interrupt to happen, and it will cause a call to the ISR. We'll stop whatever I'm doing and go to the ISR to deal with the interrupt. Fair enough? This is the end of my setup. Now I'm gonna go to the loop. And in the loop, well, all I'm doing is I'm turning on or off my LEDs, right? So imagine that this is the first time. So the first time I'm going to be turning off my LED. Good, and that's it. We're good. Or are we? Is there something missing here? Yes, definitely. We can see that we did not define what happens inside the internet interrupt service routine here, right? So we need to create our interrupt service routine. Has no parameters, returns nothing, and inside it, all I have to do is switch the state of whatever, switch the state. That's it. So what happens if I'm normally spitting out something to the LED? If there's a change in the push button that is connected to the interrupt button here, let's say we go from low to high or high to low, then we're gonna stop doing whatever we're doing here, come here, switch the state, and then once we're done with it, go back to here, to whatever we were doing here. So this means whenever I push the button or unpush the button, I'm gonna be turning on and off whatever, the LED pin, the debug pin. Alright, and here we've talked about the cause of the interrupt, right? So a change on pin number 2 will cause an interrupt to happen, and then we will go to the ISR. Fair enough. But we have different things. We can either go for the change as we talked, or we can just create an interrupt whenever there's a low to high transition. Fair enough. Or high to low, or whenever we have something going on low. And these are what the options that are available to you by the people who created this function. And remember, this is a high level Arduino C function created by people who dealt with the library. Of course, you can deal with your own and use embedded C to create your own. Deal with them in a way or another. Alright, so we talked about external interrupts, and we said that they're not the only interrupts that could happen. We can have some internal interrupts as well. However, what would happen if two interrupts happen on the same time or something like that? Good. The first thing you need to know that there's a list, whatever your data sheet tells you that the interrupts and the available interrupts using a microcontroller or something like that. You should always refer to your data sheet. And they are normally priority based, so meaning that if two types of interrupts, let's say an overflow or a counters overflow, whatever, all right, and the power on reset happen on the same time, exactly on the same human time, right? Which one has precedence? Which one has more priority? Of course, the reset one, for instance. So there are a bunch of priorities to the interrupts, and each one have an address for their interrupt service routine. All right. That's pretty much it. One can ask if we have nested interrupts, especially with the Atmega thingy here. Usually no, we do not have nested interrupts because we have to deal with the flag, right? Whenever an interrupt is happening, so the flag will be set to a value, and if it's the case, no other interrupts can happen, so we won't be able to see them, right? And however, as engineers, we can always make it happen in a way or another, but it will get a little bit more complex. I usually do not recommend that. Fair enough? Alright, and this is the last thing I want to show you in this particular recording here. So this is an example of an ISR in FreeRTOS. So basically here we're going to be dealing with different tasks. Fair enough? And this is what we're attempting to do. So we're going to have a source for an interrupt and then something to see. So we have a LED pin and a button pin. I'm creating a semaphore, as you can see here. Good. And I'm prototyping I'm not creating a semaphore. I'm prototyping my semaphore. I'm declaring my semaphore here, and I'm prototyping my task here. And the setup function, choosing output my LED pin, fair enough, and an input my button pin, we good. And apparently I'm creating a binary semaphore. So my sem here is a binary one. It's not a mutex, not a counting semaphore. Alright, so it's created empty, it's created not free, and this is for communication. I don't care for it for now. And I'm using the attach interrupt that we talked about earlier. So here we can see that where I'm referring to listen to the pin that is to listen to. No, I'm gonna detect my interrupt at the pin that I specified here. Alright, so pin number 2. This time I'm calling my ISR a handler. I can name it whatever I want. And what I'm trying to detect here is falling, so going from 1 to 0. I'm gonna generate an interrupt if and only if I go from 1 to 0. Fair enough? Then I'm creating my task, different names. I mean, name of the function of my task, the human name, stack size, and priority. We're good. Alright, so here you can notice that because we're using free RTOS, so things will never happen in the loop function anymore. They should happen in the different tasks that we have. Alright, so let's go to the task first, and then we're gonna get to the handler. Here what you're seeing is the task is a perpetual one with some sleep time. So perpetual time with some sleep time. So this makes it a what do we call it? A periodic task. Fair enough. So apparently here I'm saying that I'm waiting for the sem and I'm attempting to take the semaphore timeout set to infinite. We good? Right. So I'm waiting for the sem that was created. And the only way for me to take the sem is to someone to give it, and the someone or the something that will give it is no one but the handler that we created here. So what would happen? So this one will turn on a LUD. I don't care. This means that I'm inside the handler. Fair enough. Let's forget about this particular instruction for now. Let's go to the sem give from ISR. So remember, we cannot use sem give directly from the ISR. There's a special function called sem give from ISR, and the whole idea here is, yes, indeed, we're gonna give back the semaphore, but we have to deal with something else. All right, so you can see it here. So to make a long story short, here this is used to whatever will get unblocked after because of the giving of the semaphore. We need to deal with the priorities of the tasks that are waiting for the semaphore. Fair enough? I'm going to explain it a little bit more in a second from now. But this will, unblock the semaphore and will deal with whatever priorities we have with, tasks with different priorities that are waiting for the semaphore. Alrighty, so this means that whatever I'm removing my finger from the button, this means that I will call this, the handler will happen and the handler will unblock the semaphore. We good. Alright, so what I needed to tell you here is, if a high priority task is waiting for the semaphore and the handler made that task get unblocked, the context switch, in order to gain time, the context switch, meaning that instead of resuming whatever task we had before when the interrupt happened, instead of resuming that task, we're going to go directly to the higher priority task that got unblocked. Fair enough? This is because we're in the real-time context, and this is to gain time. Fair enough? So one last time, using that, we'll make sure that the context switch will happen before I'm done with the interrupt handler function here, or routine. Alright? This will help me gain time instead of going to the task that should resume its execution when the interrupt happened and then do some preemption or something like that. No, we're going to go directly to the task with the highest priority in the system that is waiting for the semaphore, of course. Right, so this is the end of everything related to the RTOS that I needed you to be aware of and know of.